Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Khabar semua?
Salam
Salam
doktor.
doktor, good morning.
Salam doktor.
Okay, Alhamdulillah kita bertemu kembali pada hari ini I really hope that everybody already not just watch the video but you learn the subject in the video. Okay. Boleh nampak tak saya nak share ni? Okay, boleh nampak kan apa yang saya share ni?
Nampak.
Boleh doktor.
Okay, semua yang video tu saya dah minta cover sampai example 1 kan? Betul tak?
Betul doktor.
Okay, dalam sistem auto pun saya nampak majority pelajar dah submit, tapi masih ada pelajar yang belum, ada pelajar yang tak submit. Ada juga pelajar yang buat tak habis. Okay, so saya tak faham lah kenapa buat tak habis tu. Okay, ada 3 soalan, mungkin dia buat 2 soalan ni. Okay, so saya tak faham lah kenapa dia nak buat macam tu dan apa tujuan dia lah. Okay, dan I shared already the result for the previous student. So I could say that that is the character ataupun ciri-ciri student yang dapat D lah. Okay, ciri-ciri student yang dapat D macam tu lah. Buat kerja last minute, dah hantar, lepas tu tak hantar. Apa ni, bukan tak hantar, dia hantar lambat. Lepas tu dia kata dia dah buat dah. Lepas tu auto tutup. Auto tak boleh hantar ke, tak boleh submit dekat auto. Okay, so itu antara ciri-ciri lah. Saya terpaksa cakap macam ni, itu antara ciri-ciri lah. Okay, ni baru minggu kedua, so harap menjadi pengajaran lah. Okay, masih ada banyak lagi masa sebelum terlambat. Saya cakap ni sebelum terlambat. Saya beri nasihat, saya beri amaran ni sebelum berakhirnya kelas. So ni masih bermula, saya rasa ni proses nasihat lah. Okay, proses nasihat, jangan buat macam ni, jangan buat macam ni. Nanti you akan dapat markah rendah, you akan gagal. Okay, saya dah cakap awal, saya nasihat, jangan. Okay, so jangan nak ulangi saya harap awak jangan ulangi Saya boleh je bagi ataupun boleh je untuk terima ataupun untuk ni, tapi untuk apa kan? Nanti akhirnya kalau awak tak berjaya, awak juga yang gagal, tapi submit benda tu tak dikira markah pun. Okay, tapi karakter awak tu tak boleh diubah pun, so tak guna pun. Okay, tak nak cerita banyak. So semua dah tengok kan example 1. Okay, saya percaya semua dah buat dan dah hantar. Dan dari sini what we can say, saya cuba simplifykan sikit Okay, so benda ni ataupun core ni ada nak. Yes, Amir.
Doctor, can you please speak English? Sorry for this.
No problem. I can. Just now I just make some advice to the student. Okay, not start yet. Okay, so I'm just to start.
Okay, thank you, Doctor.
I'm just to start, no problem. Okay, so I believe everybody submit and also you watch the video for the example 1. Okay, so I want to summarize ataupun highlight a few things here. The firstly, the conversion. Okay, conversion from the mechanical part. So this is the mechanical for the core, from the core. Okay, from the core to the circuit. So you can see here there is a coil. Okay, there is a coil and also the current flow. So it will represent as a voltage. Okay, represent as a voltage source. And then the other core. Okay, you need to see the core. You need to see the core. If the size and the depth, okay, the size is uniform. All the core is the same size, so it will only represent one resistor. Okay, so if the core have different size, so there will be a different ataupun multiple resistor. Okay, so for example here, so there is a length 1 and length 2. So why there is 2 length? Because of the difference in the width. Okay, so this width is only 10. Okay, for example here is 15. Okay, this one also 15. So this one also 15. And the depth is uniform, all same. Okay, so which means that this area, so you can see if I cut here, I can say I can draw like this lah. Okay, macam nak bagi kotak ni. So like this this is the area of the, when I cut here, when I cut this, so this is 15 and this is 10 cm. Okay, for this part, okay, the area something like this lah. Okay, so the depth is 10 and the width also 10. Okay, so they will consist of two different area. Okay, so this area is, I can say this is A1 and this is A2. Okay, so when there is a different area, so they will have a different resistor. Okay, so I can write here, this is R1, this is R2. Okay, so this is the like a current flow. So but this is not a current but the flux. Okay. Okay, so I believe you already know how to what is the formula. Okay, so this is MMF, so you can write like F or NI. Okay, so the calculation will be the same as the normal electronic circuit. Okay, when the resistor in series, so you just add. So R total here is just R1 plus R2. Okay, and yeah, in electronic circuit there is a Ohm's law. It's like a V equal to IR, and here is the MMF flux and also R. Okay, so this one is like current and this one is the reluctance. Actually they call it as a reluctance. Okay, so to make it easy, we can say like a resistor. Okay, so what is the formula for R, the reluctance? L M A. Okay, betul tak? So this one, so the R is L over A. Okay. So sometimes the core is like this. It's like a shell core. Shell core. So the shell is like this. So this is the core. So this is the center. So what we need to do? So this is the coil. What we need to do if the coil is like this? Tak ada idea. So sekarang core ni, now we can see the core is only like this. Okay, just like a series. Okay, now it's like a parallel. Okay, so what we need to do is we need to find the R total, R here, R on the right, and then R on the left, and then R at the center. Okay, so R at the left and at the right is parallel. Okay, so we need to calculate the reluctance using the parallel method of parallel formula. Okay, this is R L plus 1 over R. Okay, and then R total is R total plus just R center, something like this. This is the nak kira R total. Tapi tak apa, later on kita akan tengok lah. Okay, so then just calculate R1, R2, and then since in series, so just add on. Okay, and then just use the formula, so you get the flux. Okay, so the unique actually at the C question, so which is you need to calculate the flux density at L1 and L2. Okay, it's like the flux density that pass through the area at the L1 and also the L2. So the flux will be the same. If you can see here, the flux is the same. Okay, flux will be the same, but the area is different. Okay, area different, and the value for B also will be different. Okay, so if you can see from here, so firstly you need to calculate the total reluctance. Okay, what you need to do, actually the first thing you need to calculate the reluctance for each length. Okay, each length, and then R total. Okay, and then you need to find the flux. Okay, so after that you can manipulate. You can do you can calculate the flux density for B1, for B2, and so on. Okay, so itu dia punya summary. Okay, so I can say that this is the three major formula. So you need to know how to use. Okay, know how to use, not remember, but know how to use, because in the exam we will give you the formula. Okay, so if you don't know how to use, then I can't help you. So you need to know how to use the formula. Okay, so you can see here, I think in the notes they give you this one, this formula, right? Flux equal to BA. Okay, so we teach in the theory flux equal to BA. So sometimes in the example, so now in the example they ask you to measure the B. Okay, so they ask you to measure B. Okay, so you need to know how to manipulate. Okay, so sometimes in the exam they ask you to calculate the A, sometimes they ask you to calculate the flux. So it depends. Okay, maybe we learn in the class to find the B, but I can say sometime in the exam I will ask you to find the A. Okay, so later on student will say, oh, we didn't study this. Okay, it's not we didn't study, but how I manipulate the questions. So you need to understand. Okay, so therefore you need to know how to manipulate the question, know how to manipulate the formula. Same goes to the R. For example, for R, so the formula is L and then mu A, and mu also got two, right? M and MR. Okay, so sometimes I can ask you to find one of these, maybe mu, maybe L, maybe R, maybe A. Okay, so you need to know how to manipulate and know how to understand. Okay, so now we go to the example 2. Okay, so example 2, you can see here. So I read it first. So a ferromagnetic core. So this is the ferromagnetic core. Okay, with a small gap. So this is a gap. Okay, they say the length of the gap is the distance. This one 0.0 cm as a mean path length. Okay, mean path length LC over 40 cm. So this one is given already. And then the cross section area mu r and also coil number of turn are 12 cm square. So which is A is equal to 12 cm square, and then mu r equal to 4000, and then n equal to 400. Okay, it's given already. Okay, and then if the fringing effect in the air gap increase effective cross section area by 5%. Okay, so they say if the fringing effect, what is the fringing effect? I redraw here. I redraw the air gap. So this is the flux go through, and this is the flux. Okay, this is the flux, and then the cross section area. So if you can see, we take here. If you take the area somewhere here. Okay, so the area here is A, which is 12. Okay, they say the fringing effect. Okay, the fringing effect. Fringing effect something like this. Macam the flux tu macam ada curve effect macam apa dia panggil, barrel okay, barrel effect Okay, also can call it as a barrel effect. Okay, so this is fringing effect. So when this occur, so the area will be increased. Okay, the area will be increased. So this is the width for 12 for for A. So this width already increased. Okay, so if you draw, so the area will be much more bigger. Okay, the area will be much more bigger. Okay, so and they say increase. Okay, increases by the 5%. Okay, increase 5%. So if increase, so which means that the air gap is equal to increase 5%. Increase 5%, which means A plus A times 5%. Okay, so which means A is the benchmark or the starting point, and then plus the 5%. Okay, so in summary we can write is like this 1.05 A. So air gap is 1.05 A. Okay, so if I calculate so 12 times 1.05 become 12.6. Okay, 12.6 cm square. Okay, this is a air gap. Okay, so most of the students sometimes they didn't understand how to calculate the increase. They say the increase. Okay, 5%. Sometimes the student just do air gap equal to 0.05 A. Okay, this one is totally wrong. Okay, so because they don't know what is the meaning by increase. Okay, so when we say increase, which means we must have a benchmark or the first step. The first step is the A, because increase from where? Okay, so which means we have a starting point. Okay, so maybe in the exam I can write decrease. maybe I can say decrease. So if I say decrease, so decrease, for example, decrease 5%. Okay, so A gap equal to, again we need to have a starting, so which is the A decrease, so we need to minus, okay, minus A 5% times 5%, so become 0.95 A. Okay, so need to understand this one. Okay, so adalah, if you go to Google, you can say the increment calculation 100 plus percent, ada itu, nanti boleh tengok sendiri, you can go and search lah. Okay, but this is the summary. So I hope there is no issue about this. Why I highlight this one, because most of the time student confused what is the meaning of this. Okay, but sometimes when they go to shopping, okay, when they say for example the phone discount 5%, okay, discount 5% or sale 30%, so they know how to calculate. Okay, but for the exam, when we say increase and decrease, they become blur. Okay, so later on I can say discount, discount 5%, so tolak 5%. Okay, so we already know about the environment, okay, the situation of the core. So now the question, they say calculate the total reluctance. Okay, calculate the total reluctance. So the RT. Okay, so before we start, we need to redraw. Okay, we need to redraw the circuit. Okay, so we have a coil, current and current, so we redraw. So we write here NI, and then it's like a wire, and then we need to see the condition. They say the mean path length LC. Okay, mean path length LC, and already draw. So from here all the way is LC, and they already mentioned 40 cm. So which means the core is uniform, so only one. Okay, and then they have a air gap. Okay, so air gap and also core, so 2. Okay, so the first resistor or the reluctance is R core, RC, and the second one is the R air gap. Okay, R air gap. So now you can see there is a in series, so R total equal to RC plus RAG. Okay, so this is the simple formula, and then we calculate the RC. Okay, so the LC is 40 cm. Okay, so to calculate the reluctance, we must use meter. Okay, we must convert 40 to meter. Okay, how to convert cm to meter? Anyone can answer? Oh, ni kalau panggil ni memang belum tentu boleh jawab ni. Muhammad Ruzaini, how to convert? Kantul tak ada. Muhammad Ruzaini. Binila ada, Binila. Ada Ruzaini. How to convert cm to meter? Tak payah mesej.
Bagi 100, doktor.
Apa?
Bahagi 100.
Bahagi 100. Okay. So we just divide by 100. Okay. So to make easy, just move on 1, 2. Okay. So 0.4. 0.4 meter. So why I highlight this one? Because even in the university level, student also confused how to convert from 40 cm to meter. Subhanallah. Okay, we are already in the university level. Okay, the conversion, the SI unit you must know. Okay, so 40 meter here, and then the MR is 4000. Okay, and then the mu naught, we must calculate the mu naught, and also the area. Wow, sometimes become 0.00012. Okay, why it happens? Siapa boleh jawab ni? Okay, the A is 12 cm square. Okay, to convert to meter, they write here become 0.0012 meter. Why? So tadi kalau tukar meter dia jadi pindah 2 je. Ini pindah sampai 4. Kenapa? Siapa boleh jawab? Who can answer?
Sebab ada square betul.
Sebab ada square.
CM square.
Okay, it's good. Okay, so because of square, so kalau kita kalau kita tulis balik if I rewrite times 10 power of negative 2 and meter square. Okay, so meter square we need to multiply, this one become 4. Okay, so that's why they move to 4 times. Okay, this one also student always make mistake. Okay, student always make mistake. Okay, so again sometimes I can give you different units. Okay, sometimes I can give different unit. For example, LC I give you 40 cm. Okay, and then this one I give you 0.5 mm. I can give you. I just want to make you confused. Okay, I want to make sure you understand. So whatever things I manipulate, I hope that you can see and know how to manipulate. Okay, you need to understand. Okay, jangan rely 100% on example. So example all centimeter, and then in the exam also you assume all centimeter. Okay, you need to see, is it cm or mm? Okay, not only for this subject or this course, so another course also will do the same thing. They will give you different units. Okay, just to make you confused. Okay, so you calculate RC, and then you calculate RA gap, and then just plus. Okay, because of the series. Okay, and then they say, so question A already can answer easily, and then question 2, the current required to produce flux density. Flux density, the symbol is what? What is the symbol for flux density?
Pi.
Pi?
B.
The symbol
B.
for
Itu
flux
apa,
density
Doktor?
is B. And the unit is Tesla. Okay, T. Okay, the current required to produce a flux density of 0.5 Tesla in the air gap. Okay, so you need to understand, they say 0.5 T in the air gap. Okay, so which means that the B air gap equal to 0.5 T. Okay, and then they say the current, they need to know what is the current. Okay, and then we need to look at the formula. Okay, so the formula here they give you B, and then the relation is the relation have is a B flux equal to B air gap and also A air gap. Then you can get the flux. So from here, so we can use this formula F equal to R, and then F is Ni. Okay, so we want to calculate this I. We want this. The answer asks you this. So we already have the R total, and then we can calculate the flux, and then we can calculate the I. Okay. So you need to see the questions, the overall question, and then look at the formula. Okay. What you can manipulate, okay, from the formula. Okay. So I mentioned, so this is the BA gap. So you can calculate the flux. Okay. And then we use the formula, so we can get the value of I. Okay. The unit is ampere, and 0.6 ampere. So this is the current flow or current supply. Okay. So any question for this question? Belum. No question?
Okay, Doctor.
Okay. So
Tak, Doktor.
later on, I want you to copy the example 1, the example 2, and then submit to the auto system. Okay, just few lines only. Just few lines. Okay, just few lines. No need 1 week. Okay, you can rewrite. Actually, just rewrite. Understand and then rewrite. I think around maybe less than 2 minutes you can submit. Okay.
Doktor,
Yes.
nak tanya boleh?
Boleh.
Yang A air gap tu, area of air gap yang A plus 5% tu kan,
Okay.
macam mana dapat 1.05 times area? 1.05 tu macam mana dapat? Saya tak
1.05.
faham tu. Yes.
Oh, yang ni. Yang ni ke?
Ya.
Okay. As I mentioned, kan saya dah tulis kat sini kan. Ni. Ada tak saya tulis kat sini, nampak?
Ada, saya nampak.
So air gap penambahan, the increment of air gap, the area in the air gap is 5%. So this is 1.05. So become 12.6. Okay. So therefore we multiply 1.05 with 12 centimeter square. Okay. And then they get it as a 0.00126. Okay. So kena faham so you need to differentiate the area. So boleh faham sini
Boleh, Doktor.
Okay. So kita proceed So boleh clear ni, okay semua? Hope everyone okay So example T, the difficulty increase a little bit. Okay. The difficulty in example 3 a little bit increase. Okay. I could say that the question about can be similar. Okay. So they say it's a simplified DC motor, mean path length. Okay, 50. This one, this time the LC is 50 cm. Okay, the cross section area of 12. Okay, all the way the same. So A become same like previous. Then the mean path length of the rotor is 5 cm. So L rotor is 5 cm. Okay. For rotor okay, not the air gap. And its cross section area is assumed to be 12 cm. So they say same. Okay. AR 12 cm also. Each air gap is 0.05 cm each. Okay, each. So which means this one, this area, this air gap, the length is 0.05 cm, and this air gap also air gap 0.05. Okay, and the cross section of the air gap including the flinging effect is 14 cm. So given already. Okay, so the length of air gap is 0.05 cm and air gap area is 14 cm square. So it's given. Okay, it's given already. So the iron core have a relative permeability of 2000 with the number of turn is 200. Okay, the number of turn N is 200. Okay, if the current set to be 1 ampere. So given already also the current berapa ampere? 1 ampere. Find the resulting flux density in the air gap. Okay, you need to find the flux density, which means the B in the air gap. Air gap. Okay, B in the air gap. What is the B for the at the air gap? Okay, so B at air gap is equal to what? What is the formula? Flux divided by A air gap. Okay, so what we need to find is flux. Okay, we need to find the flux. To find the flux, what is the formula for flux? Okay, what is the formula for flux? Dah tak ingat dah?
F over R.
F over R. Okay, so F is Ni, and then R kita kena cari lah. So formula R is L mu A. Okay, so we need to start from the R. Okay, we need to start from R. Okay, so before we start, we need to convert the mechanical design to the electronic circuit, or we can call it as a equivalent circuit. Okay, so we start with the power system, the power and I, and then there is a one path length. So one path length. So one. Okay, so R core. Resistor ni R core. Okay, and then this one, this air gap. Okay, RAG, and then roto, RR, and then this air gap, RAG. So how many we have? So we can have a RAG1, RAG2. Okay, so from here we can say that RAG1 and RAG2 is the same. Okay, so we already know the equivalent circuit. The equivalent circuit. So now we need to calculate the value of R. So we need the RC. So we need to calculate the RC, the RAG1, RR, and RAG2. Okay, so we calculate the RC. The length is 50 cm. Okay, convert. Okay, the mu R is 2000 times mu naught, and then times the area. The area is given 12 cm square. Okay, and then we get the value, and then the roto. Okay, so 5 cm convert to meter. Okay, convert to meter. So 2000 same with the core, mu naught, and also the area also the same. Okay, and the R air gap. So length of air gap is 0.05 cm. Okay, we convert to meter. Okay, so we know that mu R for air gap is 1, and then the mu naught and times with the given area, given air gap area, which is the 14 cm square. Okay, so we know that there is a 2 air gap. Okay, so the RAG1 is equal to RAG2. Okay, so we can represent as a RAG, yeah. Okay, so RAG, and then there is a 2 area, the 2 air gap. Okay, so R total is RC plus R roto plus 2 RAG. Okay, 2 RAG, and then we get the value. Okay, the R total. Okay, so once we get the R total, so we can use this formula to get the flux. Okay, so the transfer the Ni 2000 plus ampere become 280, and then we calculate using the flux formula. Okay, 200 divided by the total R, okay, reluctance. Then we get the flux value. So when then we use the flux density, which is the B at the air gap. Okay, and area also we use the area at the air gap, and then we get the flux density. Okay. Please don't directly convert macam nak cakap don't convert terburu-buru boleh katakan terburu-buru in hurry don't convert in hurry so we need to see flow one by one. Previously I see the L, okay, the length, the path length, okay, and then I write RC, and then I look at this air gap, so RAG, and then I look at the roto, so RR, and then I look at this one, so RAG, so then become total 4 reluctance. Okay, so sometimes student when they see blindly I'm not sure why they do this, maybe in hurry, so they say RC, so RC, and then roto R, and then air gap, so R air gap, then only 3. Okay, they forgot, or they just assume the air gap become 1, because I believe why they do this, because of they refer to this example. Okay, in his mind, the example when I did in the class, air gap is only 1. Okay, so they assume also only 1. Okay, we cannot do like that Okay, we need to see the condition Okay, so different question, different condition. Okay, so everybody understand here?
Yes, Doctor.
Yes,
Okay.
Doctor.
Yes,
Good.
Doctor.
Doctor,
Yes.
kan kita kira RAG equals to 284205 kan?
RAG
Sama dengan 284,205 kan?
ni.
Tapi boleh ke kita samakan RAG1 sama dengan RAG2?
Memang sama lah ni.
Sebab dalam untuk RT nanti formula dia 2 RAG, so kita tambah times 2 kan, betul tak? Dia tak boleh equal kan? RAG1 equal to RAG2.
Bukan. Saya sama.
Saya
Bukan.
tak-
Saya maksud saya the value is the same. Faham tak? Value is the same. The RAG still have 2. Faham tak?
Okay.
Okay.
Faham tak?
So the RAG, the value is the same. Betul tak? Ni nilai ni sama, nilai RAG 1 mana tadi? Ni. The value for this is the same, the value for this is the same. So we can replace the RAG1 with the RAG only. Same goes to this one. So RAG, this one is RAG, and this one is RAG. So become 2 RAG. Not all become 1. Okay, so kena faham maksud yang saya fahamkan, yang saya sebutkan tadi. Okay. Yeah, that's why kita ada calculate kat sini ada 2 RAG, maknanya 2 ni. Okay, so itu kena faham lah. So it's good to ask because make more clear lah to the other student. Okay.
Alright, thank you, Dr.
And then yeah, during the exam, sometimes student this is the question that normally student can't answer. I don't know why. Okay. Okay, I think enough for the solution, the example. So yeah, sometimes in the exam we give you this. I can say that this condition, or this figure, this one, or maybe bukan macam ni, maybe ada macam ni. Ada gap 2 lagi. Sini ada tengah. Okay. And then how about the circle core? Okay, the core in the circle. Okay, so this is the condition that we can make student more confused. Okay. Why we want to make student confused? Because we want to test their understanding. Okay, if they understand, they can do for sure. Okay, if they didn't understand, for sure they can't do. Okay. Okay, yeah, this one is the magnetic field. So I think you also already know the permeability. Permeability of ferromagnetic material is very high. It's up to 6,000 times compared to the free space. It's like the conductivity. So in the electronic part, we call it a current flow. Okay, current flow or the conductor. So for example, the copper has higher conductivity compared to the water or compared to the air. Okay, that's why when you have a two wire, the air, okay, and then when you make a current flow, so there is no current flow because the conductivity in the air is very low. Okay, so and then you put the, for example this one, for example you put the copper. Okay, so the copper conductivity is much more higher compared to the air. Okay, so that one is for the electronic circuit, the copper current flow. Okay, and then this one is permeability of the flux. Okay, permeability of the flux. Okay, so how much current flux can flow in the core or in the air. Okay, the material of the core can be anything. Maybe can be copper, maybe can be zinc, maybe can be stainless steel, anything. Okay. Yeah, sometimes in the exam or in the theory, we always assume to be constant. The permeability to be constant. Okay. Regardless of the magnetic force applied to the material. Sometimes the current flow, okay, the current flow is not stable. Okay, sometimes they a little bit increase, decrease. It's like a sinusoidal. Okay, like I think like our house. So our house also dia punya current flow or the voltage supply in the sinusoidal, right? Voltage supply in our house, AC current kan. Okay, it's not constant. Okay, it's not constant. So even though we study in the theory, the DC current is constant, right? Okay, actually it's not like very straight line lah. Okay, sebenarnya dia ada macam ada ombak sikit lah. Okay, something like that lah. Okay, it's not constant. Okay, so we just assume to be constant lah. Although probability in constant in free space, this most certainly is not true. Okay, so it means that the probability is not always constant lah. Okay, it can be varies lah. Okay, compared to time and compared to the supply. Okay, so therefore, what happened? The flux inside the core, the relationship compared to the supply current and also the flux is not always constant. Okay, you can see here sometimes it's linear, okay, and then non-linear, okay, and then become saturated. Okay, so same goes to the flux density. Okay, so this type of graph is important. I believe there is a I think in the chapter 2 you can see much more detail about this graph. They call it as a magnetization curve. Okay, magnetization curve. Okay, so sometimes there is a linear, sometimes there is a saturated. Okay, so the difference between ferromagnetic material also will have a different effect. Okay, so for example steel X, steel Y, so there is a different effect. Okay. Okay, we try to supply a DC to the winding. Okay, winding yang tadi like this. Okay, we have a core and then we have a coil, and then we supply a DC current. Okay, we supply a current. Okay, DC. We supply DC, and then what will happen when the AC current? Okay, now what happen when we supply the DC? Okay, the DC pula. Okay, now we try AC. Okay, we try to apply DC. AC, subhanallah. We try to supply DC. What will happen? Okay, we know that the AC is a sinusoidal. Increase, decrease, negative, increase, then become positive again. Okay, increase, up and down, up and down. So can you imagine the current is increase? Okay, the current is increase, and then the current is decreasing, and then the current is negative. Okay, so this is the relationship between the current supply and also the flux. Okay, the flux. So this is F or Ni. Okay, current. So we supply current. So at the static point or at the beginning, they will start from 0. Okay, and then we supply a positive. So this one, okay, until maximum. Okay, and then the current will start to go back. Okay, reduce kan, dia reduce balik. Current reduce kan, ni current increase. So current increase until maximum. For example, maximum is here. Okay, max. So this is a max lah. Okay, and then current start to reduce. Okay, current reduce. So they reduce, the current reduce, go back lah. They go back until 0 kan. So until here. But when they go back from maximum to 0, they will not go through the same path. They will go to the different path. Okay, so they will go through to this path. So you can see here, when the current reach 0, when current reach here 0, the flux is not 0. It's not like a beginning. Okay, it's not 0 anymore. Okay, there is some value. This is a positive value. Okay, and then current keep decreasing. Okay, current keep decreasing. Current keep decrease until D here. Okay, until D, the maximum of negative. And then current start to increase back. Okay, current start to increase back until 0, somewhere here. So this one also go to the different path. Okay, flux negative, current equal to 0 at this point. Okay, and then go to up until maximum again. Okay, go to until maximum again. Okay, so you can see here, it's not like this. It's not like, the graph is not like this, not straight and then like this. Okay, it's not very straight. Okay, it's not linear. Okay, so this effect is called as a hysteresis loop. Okay, it's like a loop. Okay, this one is like a loop. Okay, this one, if I can draw, okay, it's like this. Okay, it's a loop. Okay, it's a loop. Okay, the loop we call it as a hysteresis loop. Okay, so the amount of flux is not only depend on the amount of current. Okay, the flux not only depend on the current. Okay, apply to the winding, but also on the previous history of the flux in the core, which is they call it as a hysteresis. So why not depend on the current? Because when the current becomes 0, the flux is still not 0. Okay, it's because of there is a previous flux, residual, because it as a residual flux. Okay, macam sometimes they call it, macam it's like a magnet. Okay, you have a electromagnetic for things. Okay, where you supply current, and then when you cut off the current, the electromagnetic things still ada magnet still got magnetic field over there, even though you already cut off the current. Okay, so this phenomena they call it as a hysteresis loop. Okay, or we call it as a hysteresis. So this thing might affect the flux. Okay, because when the current 0, the flux still there. Okay, and this effect also is like not error. Dia macam they call it apa macam mana nak sebut dia panggil sebagai losses. Okay, they call it as a losses. Okay, it's like a losses. Okay, so now boleh faham why does hysteresis occur? Siapa boleh who can answer? Or not can answer, but can a little bit summarize or give me some one keyword. Okay, one keyword. Why does hysteresis occur? What is the keyword? The keyword. Siapa boleh bagi tahu? Saya dah explain dah tadi. Tadi saya dah explain semuanya. So saya tanya balik, apa yang awak faham dalam yang saya sebutkan tadi?
Dia ada magnetization
Okay.
of ferromagnetic material.
Okay. Dekat dah, dekat. Close. Anyone lagi? Okay, the keyword actually is the previous, macam history ya, of the flux lah. Okay. This book is an amount of previous history. Okay, of the flux itself. Okay. Bila ada ataupun dia panggil sebagai residual error. Residual flux. Silap, residual flux. Okay. So ada flux ada baki-baki saki-baki flux yang sebelum tu. Okay. So now we go to the Faraday's law. So I believe this Faraday's law you already cover in the class, maybe in the secondary school or maybe in the foundation. Okay, so I really hope that I can go fast about the Faraday's law. Okay. I think since this one is the like a recap whatever you have done before. Tak apalah, saya proceed je lah. Okay, so Faraday's law state that if a flux passes through a coil of wire, a voltage will be induced in the turn of wire that is directly proportional to the rate of change. Okay, rate of change in the flux with respect to time. So when they say rate of change, so what happen when the magnet stay inside? What happen to the voltage? Magnet tu jalan, lepas tu dekat dalam inside the coil they stay. So what happen to the voltage?
Increase.
Increase. Okay, for example, this is the coil. Okay, and this is the magnet. So and then I move. Okay, so from the video here, so when we move toward it, the voltage move. Okay, the voltage induce. Okay, and same if I retract here. So move in, move out, the voltage will induce either positive or negative. Okay, so what happen when I stay? Move and then stay. So what happened?
No movement of voltage.
No movement. Why? No movement, but why? Kenapa?
Sorry, doctor.
Because the magnet will produce induced current.
Okay. No induced voltage lah. No induced voltage. Betul? Tu maksud awak kan?
Yes.
Okay. Jawapan no induced voltage is correct. Okay. There is no induced voltage. But why? But why there is no induced voltage when we stay at the coil?
There's no magnetic flux occur.
There's what? No?
Magnetic flux occur.
the magnetic flux is come from the magnet. There is a permanent magnet. So there is always magnet lah. There is always magnetic field.
Sebab magnetic flux tak dipotong, Doktor.
Tak dipotong Jawapan tu boleh dikatakan betul. Okay. For example, this is the magnet. This is permanent magnet, and my fingers is the magnetic field. Okay, this is magnetic field. So when I come into the coil, I passes through or I cut. This one is like I cut. Okay, this is like I cut. Okay, like cut lah. Okay, zip gitu lah. Okay, it's like cut. Okay, passes through the coil. Okay, so if I stay, so no cutting effect or there is no passes through. Okay, so that's why there is no induced voltage. Okay, that is I can say that is a how to say nak cakap dalam bahasa Melayu pun tak erti ni. Okay, how the magnetic field effect okay, the magnetic field effect in term of the Faraday's law, okay, and in term of the formula they say the rate of change. Okay, if there is no change mean zero, if no change mean zero value, no change no induced voltage. Okay, so there must be a change in the flux according to and respect to time. Okay, so that's why the formula is differentiate. Okay, so differentiation is actually it's like a change. I can say it's like a Q2 minus Q1. So this is the rate of change okay, in term of time. Okay, T2 minus T time. T1. So this one is equivalent to dq over dt. Okay, so the rate of change. Okay, it's like a macam velocity kan, so ada perubahan. Okay. Okay, and then you can see here why there is a negative. Why negative? Tak pasal-pasal ada negatif. Okay. So yeah, they say you can see this is a, boleh tulis tak kat sini. So this is N1, N2, N3, 4, 5, 6, 7. Okay. So if only one coil, so this is the formula. Okay. If multiple loop or multiple coil, so we must multiply with number of turns. Okay. So if a coil has n turns, the same flux pass through become n lah. Okay, dia darab macam ni. So then they ask why there is a negative here. Okay. So this one because of the Lenz's law. According to the Lenz's law. So for example, you punya magnet, okay, the magnet is producing the magnetic field in this direction. Okay, magnetic field in this direction, and the magnetic field or induced voltage in the coil. Okay, so they will produce a voltage. When they produce a voltage, they will produce a current. When the current flow into the loop, they will produce a magnetic field. So the magnetic field direction actually oppose the magnetic field from the permanent magnet. So permanent magnetic field is this way, this direction, and then the magnetic field induced is oppose. Okay, oppose the permanent magnet punya magnetic field. So this is magnetic field from the magnet, and this is the magnetic field induced in the coil. Okay, opposed. So that's one. They put it as a negative value here. Okay, because of Lenz law. Okay, Lenz law states that the direction of the voltage built up in the coil is such that if the coil ends were short circuited, it would produce a current that would cause a flux opposing to the original flux change. Okay, so when the magnetic field this direction and flux become in this direction. So when this direction, so gunakan right hand rule lah. Okay, so tadi ni dia rotate macam ni, dan macam ni dia terbalik. Okay, so kita tengok macam ni Okay, so there is a coil. Okay, there is a coil with few number of turn, and then this is the permanent magnet. Okay, nampak ni current ni, flux ni. So this is N and then south, permanent magnet kan. So permanent magnet. So this is the direction of the magnetic field. Okay, this is the direction of the magnetic field, the flux. Okay, and then what happened to the coil? So okay, kita dah tahu, kita tahu tadi Lenz law, the magnetic flux will oppose. Okay, so kita padam. Oh, kita guna pen lain color lain. Okay, so the magnetic field will the magnetic field induced in the coil will oppose this direction. Okay, so kita tahu the flux this direction, B this direction. Okay, oh the flux okay, and then what is the current flow? What happened to the current flow? Is it this way or this direction? Okay, so now kita nak tahu dia punya current flow. We want to look at the current flow. So what happened to the current flow? Which one? This one or this one? Siapa boleh buat? Kita dah tahu flux tadi tu. Kita dah tahu. We know already the flux. We know the magnetic field direction. Okay. And I believe I already explained in the video how to see this one. Maybe using your right hand or left hand. Which one? Which direction? Cepat. Abdul Sabik berjawab.
Ya, doktor.
Boleh jawab tak?
Doktor tanya soalan apa tadi, doktor?
Saya tanya soalan apa Itu awak tanya saya
Sorry, doktor.
Nur Fatin ada? Nur Fatin Aifa.
Ada doktor.
Macam mana direction ni? What is the direction of the current?
The right hand.
Using right hand, okay. Tak habis jawab tu, right hand ni jawab. So Muhammad Reza.
Ya, doktor.
So what happened to the direction?
Saya guna left hand rule.
Okay.
So dia punya current tu start daripada bawah and dekat end turn tu. Lepas tu dia akan naik ke atas coil.
Ni masuk dalam
dia lalulah
ni,
kat coil tu.
Masuk dalam ni macam ni, keluar kat sini. So this one is in, current flow like this
In.
And then out.
Yes.
Ini dah tengok slide apa?
Tak ada.
Okay, the simplest thing to assign the current flow. Okay, so again I explain again. So there is a coil. Okay, there is a coil, and then there is a permanent magnet move. Okay, the permanent magnet move to the coil, inside the coil, and then we know already the direction of the magnetic field from the permanent magnet, and based on the Lenz's law, the permanent magnet, the direction of the magnetic field will be opposed. Okay, when they oppose, this is direction lah. Okay, we use our right hand. Okay, this is right hand. You nampak macam tangan kanan ke nampak macam tangan kiri saya ni?
Kanan.
Awak nampak tangan kanan kan? Okay, ni tangan kanan ni tangan kanan. Saya takut video ni, I afraid the video is mirror. Okay, so this is right hand, my right hand. Okay, so this is my right hand. So the thumb, okay, the thumb actually referring to the magnetic field. Okay, the thumb refer to the magnetic field, and the fingers, the other fingers, refer to the current flow. Okay, current flow. Okay, so now the magnetic field is downward, so the current flow is in this direction. Okay, try to merge. Okay, okay, so this is like a wrapping macam this is the batang. Okay, this is the coil. Okay, this is coil, and then current flow in this direction. Okay, so betul ke tak betul tadi? So current akan flow macam ni lah, masuk sini, keluar sini. Okay, do you understand?
Doktor,
Yes.
kenapa dia masuk bawah, dia tak masuk atas?
Sebab you kena tengok, you kena pandai, you kena tengok you punya tangan. You kena tengok. Kalau dia you kena tengok you punya pen contohnya pen kan. Kalau you punya balut macam ni, dia tak kena tu. Nampak? Dia tak boleh nak wrap kat sini. Dia kena wrap macam ni. Macam tu. Faham tak? That's why saya buat macam ni daripada tadi. Banyak kali saya buat ni. So bawah tu dia boleh. Bawah tu. So the below one, we can wrap. Boleh nampak kat bawah ni dia boleh. Macam ni sekejap. I try looking my this one. Tak cantik pula nak lukis jari je. Tak payah. So boleh nampak ni? Apa aku tekan ni? So you take something. Okay, and then bawah, magnetic field ke bawah, and then you wrap macam ni. Okay, you wrap. Lepas tu you try merge, you try tengok you punya coil tu. Coil tu macam mana? Okay. So boleh jadi coil tu dia daripada belakang. Kalau ni katakan ni macam ni. Okay, ni. Macam nak lukis lagi ni. Okay, so dia datang sini. Okay, katakan nak keluar macam ni. Okay, so kalau macam ni, dia akan keluar macam ni. Faham tak? You kena tengok wrap, dia boleh wrap tak? You kena tengok dia punya coil ni. Coil ni kena tengok betul-betul. Dia wrap macam mana? Dia punya looping tu. Okay, so compare tu yang macam ni yang macam ni. Ni. So magnetic field ke bawah. Ni pun sama, magnetic field ke bawah. You tengok current flow dia macam mana. So ini current flow akan jadi macam ni. Boleh faham tak? Do you understand?
Doktor,
Yep.
kiranya semua ni dia ikut pada lukisan tu jugalah kan?
Ya, betul.
Kena refer pada figure jugalah.
Yes. Okay.
Baik doktor.
Not necessarily when the magnetic field is below, for example this one, both the same direction of B or the flux. Okay, both the same, but the current flow is different. Okay, current flow is different. Okay, it depends on the looping. Okay, so you need to play around with your hand whether it can wrap. Okay, we can wrap or cannot. Okay, so that's how you manipulate. Okay, so kalau for this one, so if this one they become for this they become positive in this way, this is negative. Okay, because it is induced. So when induced, the current will move out from the positive. Okay, so this is positive and this is negative. Okay, and for this one, for current flow out from this inside here, so positive will be the current out because of induced. Okay, kena ingat dia induced, dia bukan current supply. This one is not we supply the current. This is current is induced. Okay, so this one become like a battery for example like that become like a battery. So that's why current move out there as a positive. Okay. Okay, tak apa, it's okay. Later on when you read, you do example, you can have a more understanding. Okay. So I try to padam. Boleh nampak kat sini? Okay, you boleh play around nanti kejap lagi you boleh play around, tengok ni magnet. So magnetic field, this is the permanent magnet and this one is from the induced. So it's like this. Okay. Okay. So boleh tengok you play around nanti. Okay. So kalau kita tengok kat sini ada circle tu. Okay, tu circle kan. Circle and then magnet dia ke kanan kan. Okay. Magnet dia, permanent magnet ke kanan. Okay, nampak tak? Permanent magnet ke kanan. And then awak nampak tak video saya ni? Muka saya nampak kan?
Nampak doktor.
Okay, ni ada ring. So ni ring ring yang dalam ni, yang dalam gambar ni. Okay, saya highlight kan So ni ring tadi, ada ring and then ada permanent magnet. So there is a induced magnetic field Okay, my thumb. So ini adalah direction of current. Okay, direction of current. Okay, direction of current follow my finger. Okay, sama tak macam ni? Oh, you all tak nampak. You all nampak terbalik sebenarnya. Okay. Okay, so ni current flow. Ni current flow. Ni magnetic field. My thumb is magnetic field. And then this is the current flow. Terbalik lah. Saya nampak macam terbalik ni. Video ni terbalik. Bukan apa yang saya buat terbalik. Video yang saya nampak ni terbalik. Sekarang ni awak nampak tangan saya ke belakang jari saya ke belakang kan?
Nampak belakang tangan doktor.
Doktor.
Jadi my thumb ni dekat mana? Menghala ke kanan ke menghala ke kiri?
Kiri.
Ke kiri.
Oh, okay. So video ni memang terbalik lah. Video yang saya nampak ni memang terbalik. Okay. So apa yang awak nampak tu betul lah. Cuma video yang saya nampak ni terbalik So my video yang saya dekat ni memang terbalik lah. Tapi betul lah kalau you nampak my thumb ni ke kiri betul. Okay. So nanti you main lah. You tengok, you buat macam tu. Lepas tu ada current flow. Okay. So nanti you akan tengok sama lah macam tu. Okay. Dan bila you try oppose, dia akan jadi macam mana pula kan. Okay, so there is one major difficulty involved in using a Faraday's law equation. In practical, it assumes same flux. Okay, so yeah, they always assume same flux. Okay, so why they use always the same flux, constant? Actually, because of easy for us to design. Okay, easy for us to do a calculation, to solve the problem. It make us easy. Okay, that's why we use same flux or constant flux. Okay. Yeah, of course, in the real world, that not always constant. There is some leaking out of the flux. Okay, sometimes flux yang terhasil tu dia tak semuanya masuk ke dalam core. Okay, so sometimes the flux, the produced flux, leakage, okay, leak to the space. Okay, macam ni lah. So ni core tadi. So this is the coil and this is the flux. Okay, so the current here and the coil, not the flux not always move here, and the flux not necessary 100% move inside the core. Okay, they will sometimes go to the space lah. Okay, ada leakage. Okay, sini pun sama lah, ada leakage. Okay, so we call it a flux leakage lah. Ada leakage, the flux leakage. So the total flux will be reduced. Okay. So if the winding are tightly coupled, so majority flux passes through. So therefore we need to design properly. We need to design properly. So when we design properly, we make sure the majority flux passes through. So maybe the leakage around 2% or 3%. Okay. But if the leakage is high, okay, you can say if the leakage is high, the different expression that comes not make assumption is needed. Okay, so dia punya assumption tadi tu tak valid lah kalau leakage tadi very high. Okay, so now we assume so we have ada coil, we have a coil, and then we have a magnetic. Okay, we have we have a magnetic field, and then the voltage induced in one coil. Okay, we using this equation. Okay, when we have a multiple coil, multiple turn. Okay, so this is like a flux induced in 1, flux induced in 2, flux induced in 3, flux induced in 4. Okay, until flux induced in n. Okay, flux induced is n. Okay, so we use the I here. So if we sum up, we can get the macam seolah-olahnya multiply lah. So just now we use this one directly. Okay, and then if we assume constant, we can use multiply with number of turn. If the flux is not constant, so we need to add. Okay, we need to add 1, this one, plus D2, plus D3, okay, plus blah 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 Dn, okay, dt. Okay, so this if not constant. Okay, and this one is for constant. Okay, this one is not constant. Okay, so and then from this formula, okay, we can take out the one, this one plus 2 plus 3, okay, and then dt plus dn lah, okay, plus dn ni lah, okay, and then we can summary this one. We can do a summation. We can change the symbol like this. Okay, we use this symbol lah. So this symbol is represent this one. I equal to 1 plus until n. So this is this one lah. Okay, this is a summation. Okay, and this is, they call it as a flux linkage. Okay, flux linkage, which means that the flux in the coil 1 is different from the flux from the coil number 2, different from the flux at the coil number 3 until the end. So we sum up together, so we call it as a flux linkage. Okay, flux linkage. Okay, and the unit is a Weber turn. Okay, okay, now I want to ask, I think anyone, I believe everybody already heard about this one before, which is the eddy current. So siapa yang boleh jelaskan what is the eddy current? Amir, where is Amir?
Yes, sir.
What is eddy current? Siapa boleh jawab lagi? Ni kalau tak panggil budak-budak ni memang tak ada dalam kelas ni. Amirul Adam. Amirul macam kenal ni. Amirul. Kantul tak ada. Darwin.
Yes, Doctor.
What is eddy current?
Loop of electrical current induced within a conductor.
Okay. How it
With a
induced?
change of magnetic field.
Okay, so it happened because of there is a change of magnetic field, and then they will occur the loop of current. Is it right? Is it what you said?
Yeah. Yes.
Okay, that's correct. Okay, so eddy current. So when eddy current occur, so when there is eddy current in the loop, the current will produce a magnetic field. Okay, so you need to remember this one. So wherever there is a current, there is a magnetic field. Okay, so it's like a current in the wire. So there is a current in the wire, they will produce a magnetic field. Okay, so pernah tengok tak eksperimen magnet yang dilepaskan? There is a magnet. Macam mana saya nak buat nak buat eksperimen ni? Okey, contoh ni alamak ni tak cantik. Boleh tak? Ambil apa tin lah, ambil apa tin. Okey. Ini I think is a metal it's a metal atau aluminium kan. Okay, and then ambil je lah apa-apa kan, ambil je apa-apa, and then ambil magnet. Okay, ambil magnet. Okay, assume this is the magnet and this is the aluminium. Okay, so we know that the magnet and the aluminium is not attract to each other. Okay, so even though when you put a magnet and then you release, the magnet will drop. Okay, because it's not attract to each other. That is because of the aluminium has a very low no magnetic material lah, or no iron inside the aluminium. Okay, but when the magnet pass through the magnetic field, the magnet pass through the aluminium, they will produce a magnetic field. They will produce the eddy current. Okay, dia akan ada eddy current inside, and then the eddy current will induce the magnetic field. Okay, and therefore you will see that the magnet move slowly. Suddenly they move slowly. Okay, padahal bila kita when we release, the directly drop. Okay, but when we slide it, so you can see that the magnet slowly drop. Okay, slowly drop. Okay, it is because of macam ni, I can say dia akan ada wujud because of the eddy current. Okay, dia ada eddy current. Okay, so when the magnet tadi tu, apa aku lukis ni, magnet, okay, pass through the material tadi kan. Okay, nanti akan ada wujud eddy current. Okay, so the magnet tu slide slowly lah, because when there is a eddy current, so when there is a current, there is a magnetic field. So magnetic field also will be induced. Okay, magnetic field also will be induced. So magnetic field induced, and then they will attract each other. Okay, so therefore the magnet move slowly. Okay, so that is the effect of the eddy current. Okay, so when eddy current ada, dia dikira sebagai losses. Okay, eddy current is a losses lah. It's like disturbance. It's like a disturbance lah. Okay, so therefore when we design something, for example we design a transformer, we try to design to minimize the eddy current. Okay, we need to design so that the eddy current effect is very low. Okay, boleh faham kat sini Okay, for 1.5 and 1.6 I will give you a video, so later on you can see from there. Okay, you can watch the video. Okay, I think the video is very short about the 1.5 and 1.6. It's very short. Okay, so in the meantime I will produce the assignment. The assignment, I think the first assignment will be based on 1.3, the magnetic field based on this equation Okay, dia macam example the assignment 1 will be something like example example 1, 2 and 3 Okay, so for 1.4, 1.5 and 1.6 I hope that you can watch through the video. Okay, semua okay?
Okay, doktor.
Okay, doktor.
Okay, doktor.
Okay, yeah, since this is the second week and I believe that most of you have some time, not enough time, maybe just register to the class. So then I give chance, okay, only for this week, okay, to finish whatever week 1 revision, okay, and also whoever didn't submit, please submit, okay. I will open until 11 o'clock only, okay, 11 AM, okay. So whoever yang tak submit lagi tu, dia tak datang kelas ni, memang maksudnya memang dia memang tak nak buat lah, okay, okay. So nanti saya akan bagi video, I will give you a video and also I will give you the assignment 1. Okay, the assignment 1 you need to complete within a week Okay, so you can refer to any resources. I don't care if you want to copy and paste, I don't care, but please make sure that you understand and if you want to copy with brain. Okay, okay. Again I said copy with brain, not copy with stupidity. Okay, sometimes student they copy, they didn't see the equation, they didn't see the value I give. They copy and paste 100% from the book, from the example, from the any other resources. He forget that the value that I already changed. Okay, so that's why I say copy with brain, not copy with stupidity. Okay, so again thank you so much. Okay, I will share you a video and see you again next week. Okay, thank you. Assalamualaikum. Any ada question sebelum tu? Ada question?
Terima kasih, doktor.
Kalau tak ada kita boleh terus pergi ke video nanti I will share video. Okay, thank you so much. Assalamualaikum.
Betul.
Yes.
Ya, example 1.2 and 1.3 ni due bila?
Example, lupa saya sebut tadi kan, example pun kena hantar kan, sebab saya nak awak belajar. So example pun hantar 1 minggu.
Oh, okay, doktor.
Okay, kita akan ada example tu copy je. Kemudian ada assignment pun 1 minggu lah. Cukup tak assignment 1 minggu?
Cukup.
Cukup doktor.
Okay, terima kasih. Assalamualaikum. See you next week insyaAllah.
Terima kasih, doktor.
Terima kasih, doktor.
Salam. Terima kasih doktor.
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 Take care, doktor.
Doktor.
Terima kasih, doktor.